Good afternoon from Maine. Hope everybody's doing well. It's now August. A lot's happened. I've been wanting to redo these videos for a while now, and I have the time today. It's raining out. Actually, it was a deluge this morning. It just hammered. Crazy lightning, thunder, the whole 9 yards. In any case, these videos were posted back in February. They were very amateur. I had never done it before. I really don't know much more now, to be honest with you. The change I'm hoping is that I'll be able to go through them much more fluently, because I caught some mistakes that I said when I did the other ones. And I don't want to put this the wrong way. It wasn't as much as the knowledge was off, although I did hit some snags where I just flat out stumped myself, but just saying the wrong thing. I quoted Rodinia as being, I don't know, 100 million years old or something, and really it's closer to a billion. But just small things like that. So as opposed to trying to figure out how to edit and everything, I just decided I really wanted to record them again. So anyway, here we go. So this is 1.2 billion years of Earth history along the Marginal Way in Ogunquit, Maine, my hometown. It is a path that goes along the perimeter of the coastline from Perkins Cove roughly to Ogunquit Beach. It's an old perimeter path used by probably farmers back in the day to keep their fences up and what have you, with their properties. Because the primary area that occupies the Marginal Way is called Fraser Pasture, and well, Fraser Pasture I'm sure was a farm at one time, so that's sort of the theory that I have about it. In any case, we're going to go through two Wilson cycles, because in order to get the rocks that are at the Marginal Way today, they needed to be eroded from something. So in other words, there needed to be a mountain range there to produce the sediments that we have there today. And in order to make the mountains that made the sediments that we have today, you needed sediments from an additional source prior to that, so that the mountains could be built that again eroded and then produced the sediments we have today. So it's a chicken and egg scenario in a sense. Sediments and rock need to be laid down before it is crunched and built and thrust up and then eroded and brought to the coast. The Marginal Way rocks we see here right now are essentially Silurian, Devonian period rocks. They may even be back into the late Ordovician time. That's in around 400 million years old, or so, give or take. In any case, most of these sediments that we see were laid down in an ocean called the Iapetus Ocean, which was prior to the ocean that we see here today. Right now we have the Atlantic, but if we were to go back in time, what you would see happen is Africa would come back over to us, it would smash into us, the mountain ranges would rebuild, and then you would see Africa pull away, and then you would see pieces of North America also pull away as Africa went back across the ocean. And then you would see South America approach and hit us, and then you would see South America produce mountains, and then you would see South America pull away. It was when South America pulled away and made the Iapetus Ocean, the ocean prior to the Atlantic, that all these sediments were laid down. And they were laid down from mountains that were built from the collision of South America. We refer to it as Amazonia, the Amazonian continent, and it built very large mountains near the Quebec area, all the way down through sort of like the eastern Midwest, across the Indianas and out towards Colorado, Wyoming. Gigantic mountain range was formed there when Amazonia crushed this, and that is the sediment source for the rocks we have in the Marginal Way. So that's a lot to chew on, and I'm going to make sense of it in a little bit. But anyways, in order to get what the rocks we have here now in Ogunquit, Maine, we needed to go through two mountain building cycles, and that's what I'm going to take you through. Oh, by the way, this is the Marginal Way right here. These are the sediments that have been put down in the Iapetus Ocean that were basically derived from mountains, put into an ocean, buried about 6 miles, and then cooked pressurized, remineralized, shifted around a little bit, and then brought back to the surface after the mountains that it was under eroded away. And here's the town. This used to be a big pasture right here, and this is the path outlined, and this is a well, surfers know. Anyway, location. Marginal Way is right here in Maine, southwest area of Maine along the coast, in the northeastern United States, fairly close to Canada, and on the western side of the Atlantic Ocean. A little bit closer to home, here is the state of Maine. You have Mount Washington here. You have Mount Katahdin here, and believe it or not, you can kind of see a line going right here. And then there's sort of a line here, and maybe even something here. And then, of course, you can see definitely rock patterns here, Adirondacks here. It is all this terrain right in here that gets built up, that buries this area here under about 6 miles. And most of this area here, sediments back here were derived from North America. Sediments in this area here through here were derived from sources from the south into the east of present day, meaning that whatever was approaching and hitting here was producing sediments that went into trenches as the plate dove under North America and produced the mountain ranges. So that's how we know we had mountain building events, is because the sands here are not from North America. They match more sands from subcontinent of Avalonia. Some of them even have markers from Amazonia. So it is very interesting to note that you don't really see sands from North America till you get somewhere in here. And then anything forward of this, essentially, sand deposits, mud deposits, as this ocean closed, came from the south into the east, meaning there was a landmass coming towards us, probably a few of them, kind of like what you see in present-day Japan or the Aleutian Islands. Those are eventually going to smash into mainland Asia and create a mountain range, and that's similar to what happened here. It's close up of the Marginal Way, or a closer up of it. You get the beach right here, the path right here, and then the rock formations we'll be talking about right here. This is Ogunquit Beach, pretty much world renowned. My home beach. It's a beautiful beach. There's a lot of speculation on what's going on with that, and at some point I have done talks on the beach and the amount of sediment loss and gain that it gets over the years, and that's always a fun one to do, especially when you're dealing with a bunch of people who do not know what they're talking about that think they do. But anyways, that's for later discussion. This is an old map. This was produced by the godfather of Maine geology, in my opinion, Dr. Arthur Hussey II. Art was, I called him Dr. Hussey, but everybody, he just preferred to be called Art. He was your classic, the khaki shorts, the shirt with the pocket, but not nerdy, just more like scientist slash like mountain man, with tools in it, and this guy walked across the woods of Maine and New Hampshire and marked outcrops in the fall and the winter and the spring, and produced most of the maps that we see today that are still used by the USGS. So to say that this man is a legend is really underselling it. The man just was incredible. I met him back in 2012, and we immediately hit it off, and he basically said to me, when I'm done with this and I'm getting old, that I think you should do it. You're the only person I know that's been on the path more than I have and seems to have an intimate knowledge, and by the way, you're a geologist, so I think you fit the bill quite nicely. So that's why I like to talk about it. This is a map that he produced way back, and I forget the 1954. Wow, this is really before plate tectonics even was getting, even we even knew about it. But yet he's got some very accurate cross section. This is along this line here, sliced into the earth, and this is what you would see. It'd be like taking a sandwich and cutting it in half, and then looking at the interior. That's what you're seeing right here. And if I went and did this, would I match this? Probably not. Not to saying he's wrong, not to saying I'm wrong, but this is all up to interpretation. There's a lot of fill in the blanks in this type of work, and there's nothing wrong with that. Every person that maps something always has a bit of a twist, because we have things that we look for that, and some of us are better at other things than others. But the amount of detail that's in this from 1954 is extraordinary. So cheers to art. So the objectives of this talk: we're going to go over a geologic history over 1.2 billion years in Maine and New England. Topics: we're going to do a little review of topic descriptions and definitions used, a quick review of the formation of the planet, the creation of Laurentia. We called it Laurentia prior to about 300 million years ago, when Pangaea formed. After Pangaea comes together and separates, we have North America proper, but before that we refer to it as Laurentia. It's kind of almost you could probably name a girl that's a pretty name. We will we'll review some geologic time, the Wilson cycles, large igneous provinces, lips, Rodinia, Pangaea, Iapetus, Atlantic. Rodinia and Pangaea are supercontinents. Rodinia before Pangaea, Iapetus before Atlantic. The Iapetus and the Atlantic Oceans they're oceans. And we're going to use some modern analogies around the world around the planet to show what environments may or may not have looked like. Now, granted, because there's plant growth in some of them, I would have to say, if we're going back really far, prior to 400 million years, there just isn't any plants. So I will be hopefully cognizant of that. All right. Furthermore, emphasis of this talk will be in southern Maine, with references to Mount Washington, Katahdin, and rock formations on the Marginal Way. They are connected. Time will be focused on North America through two supercontinent cycles, Wilson cycles, including the Grenville orogeny from 1.2 billion to 950 million, and the constructing of the supercontinent of Rodinia. It is very important, because that is basically our primary sediment source for the rocks that we see on the Marginal Way. The breakup of Rodinia and the opening of the Iapetus Ocean. The closing of the Iapetus Ocean, that included at least 3 orogenies: the Taconic, the Acadian, the Alleghanian. The formation of Pangaea from 300 to 200 million years. Mass extinction, the Permian extinction event, the largest known. The breakup of Pangaea, which is from 190 million to 174 million, and the opening of the Atlantic Ocean. The Mesozoic period and the KT extinction event, the Cenozoic period, the Pleistocene, which is the Ice Age that basically really shaped what we see in New England now, and then the future of the North American coast. This is the geologic time scale. It's supposed to be a circle, but I stretched it so it's more of a donut. But in any case, you can just get your idea of how giant time is. I mean, most of everything that happened in North America here along the East Coast occurred right here and on. Basically we're mostly Paleozoic rocks. When I say that the Grenville was important, the Grenville orogeny would happen back here. But what this did is this produced the rocks that allowed the Appalachians to be formed. The Appalachian Mountains are formed from a mixture of rocks from the west and rocks from the east. The rocks from the west came from the Grenville orogeny. The rocks from the east came from approaching continents. But you would have no sediments for some of these without the building of the Grenville orogeny, between 1.2 and 950 million years ago. So they were formed around here. We have a period of erosion, and then we have rifting, and then we get to here, and then the Iapetus Ocean begins to close, and then we start getting sediment sources from the east as well, to start creating the rocks that are basically form New England. And then Pangaea comes together here, and then splits right here, going into the Mesozoic with the dinosaur period, and then this is the time of mammals and humans. I mean, we don't even register here, so it just shows you that, life really didn't get going till about 10 o'clock, 10:30 on the scale here of a 12-hour day. For the most of it, it was pretty much lifeless or single-celled organisms. Yeah, the multi-cell organisms, yes, we do have evidence of that now. But just to give you an idea, Earth time is very, very large. Long, I guess would be more of an appropriate word. This is time as a clock, and again, I was saying that life really didn't get its act going until, or at least complex life, until about 10:10. Well, I guess here it says about 10:10, but between 10:10, 10:30 is when you start to really see complex life start to come out. Oh, I'm sorry, that would be, yeah, at 10, about 10:30. In any case, yeah, just gives you a better perspective of how much time there is prior to, and believe me, life did kind of kick off down here, but we remain very simple single-cell organisms until sometime over in here, where we became eukaryote cells and we became multicelled, and then we sort of lived through that, and then right around here is when some things started to happen. The multi-cells began to stack themselves and they began to come together. So not just multi-cells, but multi-cell colonies came together here. So kind of an interesting part of evolution. And this is really shows you. So again, life is here. You really need to go, whoop. This is like a terrible ski line. We have to go through all the little poles and the ropes and everything like that. So again, life is here, but you have all of this back here for Earth history, where there's just nothing that is macroscopic. Like, in other words, you can't see this type of life form to the unaided eye for the most part. So anyway, I just like to get that point across of just how long time really is. And again, our story is kind of beginning around here with the Grenville orogeny, more or less about here. And again, an erosion period of erosion right here as the Iapetus Ocean opens, and then it begins to close right around here. And again, most of this time you're getting sediments along the North American border around Vermont, probably out to New Hampshire line, and that's all sediments derived from Grenville orogeny mountains to the west. And then after that, I keep going on this point that as the Iapetus Ocean closes, we are going to see sediments start coming in from the opposite side as a landmass begins to close and approach and close that ocean. And that's one of the evidences that we knew something that something collided with us from the east. This is just a very detailed, gigantic, so much stuff involved map. It's a beautiful map. My only beef is that it doesn't really display the times correctly, because this should be really 3 of these, and then this whole area should be 1. But anyways, it's just trying to, because we know so much more. The further back we go in time, the less we know. So it makes sense that the chart's going to get more filled up with higher details as we approach present day, which is here. The beginning is here, present day is here. And so you've got sea levels changes and continental cycles and magmatic, the pole orientation here reversed, traditional sea level, the whole 9 things. So in continental locations and stuff like that. So it's a wonderful map. If you can blow this up and put it on a giant wall, man, you would really not have to reference a lot of stuff. But anyway, I just wanted to bring that out. All right, so planet formation. It's important to know how the planet formed, because if we don't, then really everything else is just not going to make a lot of sense. But sort of the basic tools on how we see how the planet forms and the history of it is we need to locate certain things. And things that we look for are eroded orogenies, which are eroded mountain building episodes that existed once that are not there, and then basins basins are where things collect. Basins are oceans, orogenies are mountains. We look for ancient evidence of both of these, because when there's an ocean formed, and there's land around it, all the sediments from that land are going into the ocean. So they're intimately connected. So as a mountain range erodes, the oceans are collecting it. And these two go hand in hand, and you almost always have one with the other. And Maine is no exception. In Maine, we see the erosional roots and the granites of the basement rocks of mountain ranges, and then we also see the sediments on each side. And we see these in Vermont, we see them in New Hampshire, we see them in Maine. And think about Katahdin, we see granitic rock right there, Sebago. All of these are granites. The central and northern part of New Hampshire, loaded with granites. And these are caused by upwellings as a plate was being subducted under New Hampshire and melting, and then producing buoyant lavas and magma that either got lodged into the crust and solidified or blew through and created volcanoes. And New Hampshire has evidence of both. So these are our tools. So when we find old areas of this where there's no longer mountains, well, something had to happen there, because this doesn't just form on the surface. So those are just some of the tools that us as geologists use in order to figure this out. All right, so real quick, Earth pretty much came together about 4.65 billion years ago, 4.6. Right around there. It seems to always get a little bit older, but I guess here we have 4.54 to 4.338. And this is what we call the time of accretion. And at this point, Earth is basically, the sun has now ignited. It has blown off a lot of the lighter gas, like hydrogen and helium, which, it kind of makes sense that Jupiter and Saturn, which are mostly hydrogen and helium, are located where they are, because that's about the distance that the solar wind, when the sun ignited, would have blown that gas. The heavier stuff is harder to blow. It's like if you put some rocks, some sand, and some dust in your yard and take a leaf blower and give it a blast, well, the rocks are going to stay, the gravel might roll, the sand's going to definitely tumble, and the gas is going, and the dust is going to just fly out to a much further area. Well, when the sun ignited, the solar system did the same thing. So the heavier stuff had a tendency to stay closer to the sun, the lighter stuff go on the outside. And so when that happened, things were already beginning to come together prior to this. But now, it basically, as opposed to just having a dust cloud of everything, you only had certain things. You didn't have all the hydrogen and helium anymore. You had mostly silica and CO2 and oxygen and just heavier stuff. So what happened is that as the planetesimal of Earth was spinning around through the dust cloud, it was collecting more and more and more stuff. And as it got bigger, it had more gravity, and it started to just, it's like a runaway effect. The bigger you get, the more you're going to collect. So Earth just kept growing, it kept getting bigger, it kept grabbing stuff, and it began to become a planetesimal, and then it actually became a planet. And we know that in space this happens because the shuttle astronauts proved this by taking 2 grains of salt in a zero gravity environment out of a bag, and lo and behold, those 2 grains found each other. They didn't need anything except for their ionic charge to figure out where they were, and that's all it takes. Things will find themselves in a vacuum of space. And so now that we know that, it makes perfect sense of how this would have happened. So for about 4 billion, 4.5 to about 4.1 to 3.8, somewhere in that area, or 4.1 we'll just say, the Earth spun around, it collected a bunch of rock, it began to actually differentiate, meaning that the iron, because the Earth was really a molten ball of rock. It was just molten. Heavier stuff went to the center, lighter stuff, sort of like an onion, stayed on the outside. And the Earth basically bubbled and cooked and differentiated and made these layers. And over time, the crust actually began to cool. However, because every time something hits the Earth, it releases a massive amount of energy, the Earth remained molten longer than it normally would have, because every time something hits the Earth, it's giving more energy, and that energy accumulates in the planet, and then the planet needs to get rid of it, and it does that through radioactive decay. And it just takes time. And so we think by about 4 billion years, there were pieces, there's definitely pieces of crust that had formed. We did not have continents. We probably had areas that were still molten, but by about 4.2, we're pretty sure that we had a crust. But it wasn't like anything we really, it was probably very mafic, very dark. And it really, it was fairly iron rich. And it was just a hellish looking place for the most part. And then over time, around I think what was the time period on this? I always get this. Yes, around I think around 4.1 to 3.8, we have a period of time called the late heavy bombardment stage. And what happened was the outer planets shifted. And we're not really sure if Uranus and Neptune actually formed between Jupiter and Saturn and then migrated, or Uranus and Neptune just switched places. But we know something shifted out there, and it caused a lot of comets in the outer solar system to get knocked out of orbit and come into the inner solar system. And they whacked everything in the inner solar system. You can see evidence on the moon. The biggest craters are caused during this period of time. The Earth, with no doubt, had even more of those hit. And during this period of time, we think that the late heavy bombardment added an additional, I don't know, I don't know the exact number, but maybe we'll say 10 to 20% more mass to the Earth, as well as providing it with water. Comets have a tendency to have a lot of water and ice on them, so we think that may have really contributed to how the oceans, really came into existence. Although we do know that we did have some form of ocean slightly earlier than that. And at some point, I did not mention this, but at some point, you really have to wonder, okay, where'd the moon come from? Well, the moon was basically struck. The current theory is that the moon is a result of the Earth, the Earth being hit by something of a Mars-sized planetesimal planet, that basically was a glancing blow, and it stripped the outer layer of the Earth off, and blasted some of it into space, where some gravity alone was able to hold on to a good chunk of it. And basically it began to coalesce in an orbit around the Earth, and basically had the moon. But what's interesting is that we know it was sort of a glancing blow, or at least the evidence that suggested is the fact that for the size of the moon is very silicic, where it should have some more heavy elements, and for the size of the Earth is more mafic, meaning it has more iron because it's deeper in the crust. So in other words, the outer crust of the Earth was more silicic, and that got stripped. So we lost the outer onion layers, whereas the inner onion stayed. But then they had to, more or less come up and replace the shells that we lost. So you have more mafic material the deeper you go in the Earth's crust, whereas the moon had very little mafic material because our crust at the time when it first formed had more silica in it. So in other words, the moon is more silica rich than it should be for its size, and the Earth is more iron rich than it should be for its size. And we think that has a lot to do with the impact event at a glancing blow. Had it just really was a dead hit and blew everything apart, and then it had to come back together again, likely the Earth and the moon would have a very similar composition, or at least they'd be more. The moon would be more iron rich, and the Earth would be more silica rich. So, in any case, that's the Hadean period. Then we go into the Archean period. We generally put that at about, it says 3.8 to 2.5. It's more or less 4.0 to 2.5. And at this point, the Earth was still very hot. We did have crust by about 4.0. We had evidence of crust even differentiating a little bit, and it really is after the late heavy bombardment between 4.0 and 3.8 when we get the additional impacts. We get the oceans really coming into high gear, and it's during the Archean time that the crust really does its first more or less differentiation event, meaning that the crust begins to form, it itself begins to put heavier stuff on the basement, basically your iron, your heavier elements on the bottom, and then your lighter, more silicic elements up above. And as the outer crust began to cool, lighter elements come out first. The heavier elements stay more liquid, so of course that helps them sink further. And you end up getting areas as the crust cools. Repeatedly, you get more silicic melts, which are basically, silicic type rocks like granites. And then you have mafic type rocks, which are like basalt, which form the crust, the ocean crust, the lower crust, and then the more silicic forms the continental crust, which is more buoyant, so it floats. And then over time, it is during this time that these pieces of more buoyant granites and more mafic pieces of oceanic crust that slam into each other, forming island rocks, end up slamming into each other, and they form the first cratons of the continents of the world. So in other words, it was during from about 3.8 to 2.5, 80% of continents was formed, or the nucleus of these continents was formed during that period of time. And it was all from crust melting, running into each other, heating up, remelting, and every time you had a melt and reheat cycle, you're taking out the lighter elements, and the lighter elements end up staying high up on the crust because they do not subduct, so they end up basically just getting bigger and bigger and bigger, whereas the oceanic crust dives underneath these more buoyant continental pieces of rock. They in turn melt, they in turn interact with the continental cratons, causing now mixtures of melting, and you have all sorts of different types of rocks forming. You have intermediate rocks, you have felsic rocks, you have mafic rocks, and again, these are all smashing into each other, and they're forming the nucleuses of the cratons of the planet, and that all happens in the Archean period. And if you wanted to look at early Earth, you might think it might look something like this. Lots of volcanoes, lots of subduction. I'm not 100% on this, but we know that one of the oldest life forms on the planet, the stromatolites, showed up in the Archean, and this looks to me like a batch of a bunch of stromatolites. They're basically primitive algae mats that just grow. They kind of accumulate they grow on top of each other, and they make these mounds that turn into rock. And they're everywhere in the fossil record. They're still alive today. They live in Australia, and this is very early primitive life. You got the moon much closer, probably at least a quarter closer, or a third than it is now, so it's much bigger in the sky. The fact that the sun and the moon cover each other is just coincidence, believe it or not. There are very few true coincidences. That really is one. Volcanoes going off, what have you. And of course, the ocean's probably a different color. We do not have much of oxygen yet, so the ocean's either I think it was kind of like a purple, dark purple or something like that. I don't know, it looks really like a weird green here, but it's definitely not the ocean you'd recognize today. So again, I'm going to mention the Archean period, about the building of the cratons. This is a little graph right here that shows this is time, this is present day, Phanerozoic, Proterozoic, Archean. And this is the chart of the continents. And as you can see, close to 80% of continental growth occurred in the Archean period. So the Earth, think of it this way, the Earth was so much hotter. We know that because there's different types of volcanic and igneous rocks that are produced during this time that are no longer produced today. So that's one of the big pieces of evidence. The comatites are super ultramafic. They melt at something like 1600 degrees, or I don't know, it might be higher than that. But they at 1600 is a number that stands out. It might be I think that might have just been the average. That was the temperature of an average. I just know that the Earth was hotter, and these comatites, if they exist, they're much deeper in the Earth now. They do not make it to the surface. In any case, that's one of the evidence that we use to say that the Earth was definitely hotter. But the crust was thinner. It was hotter. It was probably more putty-like. So things probably moved very quickly on the Earth's surface. And I don't believe there's a huge debate in our world, in the geologic world, about this, about the tectonics, and were they like they were now, or were they different? And I have a tendency to believe, just by the amount of accretion that happened alone, that they were A, faster, and they were B, the crust was much thinner, and it had a tendency to stack much better. And I don't think that you had very high mountain ranges because the crust was just too thin to support it. So there's a term called for that, we call it I think it's a, I don't want to say stagnant lid, but it's basically you really have more drip tectonics as opposed to actual subduction and underplating, I think. But that's for, I don't think many people would understand. What I'm talking about is that you have a blob of continental mass or something, and maybe the bottom stays hot enough where it just pieces of it drip off and drop, or old ocean crust that had formed gets heavy and just drops and then gets reassimilated and pops back up, as opposed to things diving under each other. They may have just collided and melange themselves. I'm not really sure, but there's a lot of evidence that true modern day plate tectonics was not really quite active back at this point. And there's a lot of evidence for that. One in particular is most subduction zones have a tendency to have blue schist facies, metamorphic rock types, and we do not see those until about 800 million years ago. So there's a couple spots, but they really don't start. You start seeing them much more later on, after about 800 million years. So maybe that's evidence that it just wasn't happening like it is now. So anyways, this is the crustal line. Start with 0, and then you go up to 100%. This is, what am I looking at here? Yeah, this is the first cratons. Again, sort of the same graph. Archean rocks, you got gneisses. This reflects fairly high level metamorphism. You have greenstone belts. Greenstones are areas of metamorphic rocks that are either very mafic or they're oceanic crust. And the oceanic crust is basically areas where it just got squashed or pinched, and then it got buried, not reheated. It just got pressurized, melted, and turned into greenstones. Granite is areas of the crust, melts that are above the collisional zones. So the granites are basically associated with continents. Greywackies are just muds that are thrown off from the island arcs as they approach, or they erode. And chert is precipitation of silica in the deep ocean. So when you get chert, it's just telling you that there's an ocean. You can't get chert without ocean, so that's kind of important too. And shallow water sediments are rare, basically saying that their continents did not have passive margins. In other words, you don't have a nice east coast. You got basically a California coast, which is or an Indonesian coast, which is just like straight down to 10,000 feet. Craton locations today from the Archean period. Again, I said that at that time, that picture we had stromatolites, and here they are. They still grow today in a place called Shark Bay, Western Australia. So craton locations today. If you look at a map, you can see we got a big chunk up here in the Canadian Shield. We got a big chunk of it here called Amazonia. We have it here in the Greenland is made up of mostly a Canadian Shield. You have Western Africa, you got South Africa, you have Baltica here, India here, Siberia here, Pilbara here. I forget the name of this one, but this is the Chinese one here. But these are, Madagascar is actually part of this. These are all areas of the cratons today. Anything that's not yellow, I guess you could say, is essentially, well, that's not true. It's anything that's in this black line would you consider Archean cratons. Okay, so that would make more sense. The other stuff, I believe, is Proterozoic. And that's what we're up to now. So the Proterozoic is the real granddaddy. It's the largest of the eons in time. And if you want to think about it, the Hadean was a period of the time of the coalition of the Earth. Everything was hot, melted, not really, bubbling, churning, and maybe a few pieces. The Archean is when the crust really got solid, and it formed the nucleuses of most of the continents as we know them today. And now it's the Proterozoic period where everything gets switched. So it takes about almost 2 billion years to take a barren, rocky, pretty much single life form celled organism, like uh, uh, to take it from that into life forms that actually create bone and skeletons and can be found in the fossil record. So it takes 2 billion years of basically, maybe more, of single-celled organisms to start becoming multi-celled, and then even multi-layered, and then actually forming, systems enough to form an organism. So it takes a very long time, and that all happens in the Proterozoic period. And the reason why is because it's during this time that the Earth has cooled off enough, and that we have the stromatolites, eating up carbon dioxide, producing oxygen, which is helping to make the Earth cool down, because before there was just so much CO2, the Earth was hot. Now these stromatolites are eating this up and they're cooling the planet down. And it really happens in this time, and by about, I think it's 1.8 billion, we get what we refer to, I don't want to say that number, is it 1.8? Well, it may not be 1.8. I think it's 1.8. All right. Well, in any case, at some point, we get at what we call the great oxidation event. It's hard for me to say. And what happens is, for the most part, we do not have much oxygen in the atmosphere. Present day is like 21%. But it took a long time to get there, and we didn't even get that high until Paleozoic times, really. But at the beginning of the Proterozoic, it's safe to say, I don't know the exact number, but I'm certain it's probably less than 2%. But it's at this time, during this time, when we get a huge event called the Great Oxidation Event, which really boosts our O2 up. It allows the ozone to form, all sorts of things going on. And we know that there was a lot of oxygen happened at this period of time, because all of a sudden, all these new minerals start showing up that involve rust. And rust is oxidation of minerals. And prior to the Great Oxidation Event, you don't see it. So something happened, tons of oxygen was produced, and that changes everything. That is a game changer. And for certain, the stromatolites, they had, definitely had something to do with it. They were eating up CO2. That was how that's how they formed energy, and then oxygen was the byproduct. So, but yeah. So, yeah, the Proterozoic is a time of changing the Earth from a place that's completely alien to something that we may even recognize today. All right, so Proterozoic eon. Here we go. This is early Laurentia. In the Proterozoic eon, we have numerous orogenies that occur around the perimeter. We also have deformation of the shields that originated in the Archean, and we add definitely some real estate to the early North America. Outcrops of the rocks that we see from that period of time, from the Precambrian, you see them exposed up here in the northeastern Canada because of the latest glaciation, and we call that the shield. If anything's buried, but when we infer this from oil drilling and all that stuff, so the platform is here, and that is just an extension of this part. These are the deformed areas that occurred after the Proterozoic. These are more or less Paleozoic rocks. This basically shows the different pieces of cratonic crust that came together in the orogenies that happened for them to weld together. So in other words, these sort of purplish pieces are the oldest right here. Boom, 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 boom. And then you can see this green right here. These pieces came together and created this area right here. And this is the area between these two and this right here, and this right here, and this right here. That's a trans-Hudson orogeny, and it happened because these two pieces slammed into each other and created this area right here. So this area right here is welding all this together, and those are orogenies, and that was evidence that these were separate at one time and then collided, because here's the old mountain range right here. And this, in the Proterozoic, we have a supercontinent called Rodinia, which I'm going to discuss later. And Rodinia kind of looked like this. So you have South America here. You have can't really tell what that is right there. It's probably, so I think Siberia is over here. You have Antarctica here. I'm sorry, Antarctica here. You have Australia here. That looks like West Africa. This is not sure what that is. In any case, there's West Africa there. This is Rodinia, and as I said, we had a part of South America, Amazonia, along the east coast, and here it is, right there. Like we would be somewhere in here, and where it's right up against us. And this is the orogeny that gave us the materials to start to build the Appalachian Mountains, or at least parts of them, the western parts of them. And this is it's known as the Grenville orogeny, and you can see it again right here. But yeah, interesting stuff. So no talk about doing this type of stuff is complete with plate tectonics. Sorry, talking all this makes me very thirsty. I mean, if you're watching this video, I'm assuming you're familiar with plate tectonics. If you're not, that's okay, but it's going to be an eye-opening experience if you've never heard about this before. Anyways, so you have oceanic crust here diving under an island arc here. So this would be kind of like, you could say like Japan, or this would be the Indian Ocean going underneath Indonesia right here. This would be Antarctica coming this way. So, and then there's an island arc right there, which would be Indonesia, trench, accretionary wedge, Indian Ocean, Antarctica. And then if you were to go all the way around to the other side of it, at some place you're going to find a spreading ridge. This is like the Atlantic Ocean right here. This would be Africa, United States. And there's a spreading ridge right here. These are not definite. When I say that I'm representing these pieces of land as certain places we know today, I'm not saying they are. I'm just saying that that would be the modern analogy. So, in other words, yes, if you look at the Indian Ocean, if we were to use this area as the Indian Ocean, you have Antarctica, Indian Ocean crust subducting under Indonesia, and it produces very violent volcanoes. You have back arc extension here, and that's sort of like, Taiwan and that area back there. And so when you look at the Indian Ocean and go right behind it, between where the Philippines are, or Taiwan, or near Southeast Asia, you have another area that's sort of like a shallow sea, but it's getting thin, and the crust is thin there, and that's why you have that sea, because this is diving, it's pulling everything this way, and it's kind of stretching this area right here. Now, scratch this, and then take this and have this represent Africa, and this is the United States, or let's just say Africa and South America. You have a mid-ocean ridge of the Atlantic Ocean. Upwelling is coming here. The crust is being pushed this way. Crust is being pushed this way, and this is a separate area. And this is the lithosphere down here. This is crust. This is more like putty. And then you have the mantle right here. And this is probably the thickest layer on Earth, and it's just plastic. Molten materials that's always mixing, all sorts of stuff's going on down here. It gets more mafic the deeper we go, and then you have an iron nickel core. And this process, this is eventually going to smash into this, and then this is going to get welded onto this, and this will be new real estate for this particular piece of crust. This will eventually stop this, and then this will end up shutting off, or a trench will form here, a trench will form here, and then these will come back together. Wilson cycles. All right, so this whole thing right here is basically summarized in this diagram here. So let's just start. Here. This is here. This is today, Africa, North America. We have an active spreading ridge. This is the Atlantic Ocean. Things are going this way. Things are going this way. We have passive margin, passive margin. Eventually, in another, we think maybe 50 to 100 million years, because the Atlantic Ocean is a fairly successful, large spreading center, that it's going to get much wider, and then it's going to look something like this. You're going to have tons of, more sediments, sands, and stuff forming, and this will be mature. It already is. It's really the Atlantic's between this and this. It's probably right here, but anyways, this is when it finally gets to its largest extent, and then at some point, and this is kind of going out of style now that it just mysteriously appears. It's possible that this does get heavy enough or the sediment loads enough for subduction to start, but why exactly subduction starts on one side or the other is kind of a mystery, but we think it may have something to do with transform faults that are in the Atlantic, and that's very complicated. I'm not going to go into it, but anyways, at some point, crust will start subsiding underneath one side or the other, and in this case, it's subducting under the African side, and one side remains passive. And what happens is, as this subducts, it pulls the whole ocean crust over, and eventually even subducts the mid-ocean ridge. And then this piece here gets welded onto this piece here, and it looks something like that. And this is the beginning of a sort of a Andean, not an Andean, but this is the beginning of a Himalayan, or maybe like the Alps orogeny. And then you have basically everything collides and stacks and gets super heavy and bows down the crust. And this is your Himalayan style mountain range. And then eventually this erodes, and then you get decompressional melting under here, because even though this is super hot, it's been held down like a lid, like a pressure cooker. But once you take this erosion off and send it out here, this gets lighter, this comes up. This begins to pop and fizz like the shaking and the removing of a cap of a Coke can. Think of it that way, or a Coke bottle. And then the two halves begin to separate, because you have the melting, the crust melts, then the continent gets thin, and one side goes this way, one side goes this way, and then the whole thing starts over. And this is a much more detailed description of what I just what I just discussed. And I will go through it real quick again. We will start here. Atlantic Ocean today, nice and blue. Active, lots of spreading here. The Atlantic Ocean is just cranking. Africa going her way, North America going our way. Very hot, lots of lava, all sorts of magma coming up right here. Again, one side or the other will get subduction will start. One piece will go under one side of the continent. It will drag all the crust over, and eventually this side here, which is now here, gets pulled over and slammed into this offshore island, this island arc that forms along this side. And this would be something like, really where we see this today is you kind of see it in Japan. You got an island arc offshore. The ocean's, well, that's not a good example. Yeah, I'm trying to think exactly where the Aleutians are like this, except that the land is much further away. You know what I think that yeah, it's weird, because I guess what you could say is maybe the Philippines going into the island arcs behind it, because the Philippines are definitely on their way over, and they're going to smash into Asia, and then there's an island arc or two in front of them. So that would be more into. But in any case, and Puerto Rico's kind of doing this too. Not Puerto Rico, but the West Indies there and the Lesser Antilles is an arc like that. But in any case, one way or another, this gets slammed into this, and this gets welded onto this. And then you have a collisional orogeny right here that looks like this, and this absolutely happened here in New England. Like, this whole series right here happened. So a good analogy of this would be the Cascades of the Andes. You've got both active island arcs, and they're fairly young. They're not that old. And then once everything gets shut off and there's no more subducting of crust, because the ocean crust is really producing the lavas to make these arcs. Once that's down and the crust gets super thick, nothing can really punch through, and you do get some intrusions under here, but they don't make it out, and they basically suture basically they stitch the suture together. So this is the suture between here and here, it's here and here, and these end up basically stitching all this together. This is what's left of the oceanic crust. That'd be an oophilite, and the Himalayas are basically what, you know, a good analogy of that. Now the Alps were higher than they are now, and they are older. But the Alps stopped colliding, and then they began to erode, and now they're unthickening. And then the Alps are probably one of the fastest eroding mountain ranges in the world. Like, there are places where they're just falling apart, and that's what's happening here. The root has now melted because it's been lifted. Temperatures were allowed to melt it, and you're going to start getting basically thinning here, and this is going to start being driven apart. But before it does, it will become a rolling flat land. This really should probably go up like this, because this is going to really start to undermine eventually. This is like the Great Plains that we see today, and they will eventually, you know, and it's tried before that, where the continent of North America has almost split apart a few times. And eventually, under this, you're going to get, this is going to start to thin right here, and you're going to start to get melt, and then the whole series starts again. And this was represented by the, you know, this is like the Gulf for the Great Plains or central Canada. This is like the opening, this is what the opening Atlantic would have happened. You see places like this in the Red Sea, Eastern Africa, in North America, Connecticut River Valley, Newark, the Newark Basin, like all of that, those are rifts that were started to erupt as magma started to come in here, but they didn't make it. In other words, in the Connecticut River Valley it started, but then the actual opening went to the east a little bit. So anyways, that's the Wilson cycle. And we're going to stop here, because in order to split continents, you need these large igneous provinces. And they aren't like Mount St. Helens, they aren't like Mauna Kea, Hawaii, Mauna Loa, Hawaii, or Kilauea. They are not like Yellowstone. They are much, much, much bigger. They undermine in complete continents and split them up, and they are a huge part of our evolution and our history, and those will be for the next lecture. And thank you for watching. Aloha.